Welcome to lesson 20, where today we are looking at applications of the factored form. So again, this is also review, but today we are seeing now some examples that look different from the ones we've seen before. So looking at this first example, we are told that some students are selling t-shirts to raise money. And we know that from their previous year sales that they have some statistics. So they know that they can sell 40 t-shirts a week if they sell them at $10 each. And if they raise their price by $1, they will sell one less t-shirt each week. So if they sell it for $11 that week, they're going to sell 39 t-shirts. So they pick some random price options and try to estimate their number of sales, uh, as well as to calculate their revenue based on those number of sales. So if we have our $10 price, we sell 40. That's what we were told. Now, if we add $5 to the price, if we add $5 here, we will be making 5 fewer sales, so 35 here. And then our revenue will be the price of the shirt times the number of sales, and that's that formula you have at that bottom, 35 here. So this will be 525. And then the rest of the table would be filled out as such. So here we have 30 times 20, or I'm going to follow that same format. So 20 times 30, and then 25 times 25. And the reason I switched my order is now you can see these growing by 5 and these decreasing or shrinking by 5. So here is now where we are going to see the main difference between this problem and the problems we've seen so far, where you are now not being asked to determine the ticket price or the number of sales. You have both of those, but there is changes that's being made to them that will affect our revenue. So here we have X representing um, every $1 decrease to the price. Oh, sorry, uh, increase. And that way, we know that if this is the price and this is the number of sales, then every time we add X to the $10, we are losing X in our weekly sales. So now we have a factored form. It does look a little bit different because X is now the second term, but you can easily rearrange this to have X as your first term. And that's a formula for our revenue. And now we're told that another solution to this problem is given by this equation, and we're asked to verify algebraically if these two are the same. So I'm going to start with that factored form. So I'm just going to rewrite it here. So 40 minus x, and then 10 plus x. And what I'm going to do is I'm going to expand this. So, and I'm just going to keep it in the same way, same order for now, and apply FOIL. And you'll see that FOIL will still hold. You do not need your correct order. But now maybe I'm going to rearrange it where I have x squared plus 30x. And, oh, this should be negative. 400. And we see that this is the same as that equation. So yes, they are the same. So now you are asked to use the quadratic formula to verify this as well. So here, first I have factored out -1 to get that a value of 1. So now I applied the quadratic formula here for you. So -b plus or minus b squared minus 4ac divided by 2a, which a is 1 in this case, so just 2. And you will get 30 plus or minus 50 divided by 2. And if we calculate this, we get that x1 is 40 and x2 is -10. So then, if we were to write this in factored form, we would have, we'll just rewrite that equation here. So this one in factor form will be x minus 40 and x plus 10. And now, let me copy this out here. We also want to verify that these two are the same as well. And right now, right away, they don't look quite the same. So I'm going to go from here and I'm going to expand this -1 into this bracket. So I get negative x plus 40. And you only have to do it once here. We're not multiplying by both brackets because multiplication is we're multiplying this by this by this. So once you've multiplied these two, you're not multiplying it here again. Okay? So that would be it. And here we have that x plus 10. And one more time, I'm going to just rearrange these. So with addition, we can just reverse their order here. So 10 plus x. And now we see that these two are equal. So yes, we can also get our answer using the quadratic formula by finding the roots and writing the factored form and then expanding to the standard form depending on what the question has asked us. And in all cases, your answer will be the same and you can always algebraically verify or use graphing tools to verify your answer. So our next example here, we're told that the height of a ball thrown in meters is given by h of t. And so the ball is being thrown from a cliff, and our time is in seconds. So we're seeing the height um, in meters. So let me just set up my graph there. So h of t in meters over t, our time in seconds. So first, we're asked to identify the zeros. So the zeros we get by setting h of t to 0. So then we know t of 1 is either 0, which gives t is 1, or t minus 4 is 0, which gives us 4. Sorry, slight error there. That should have been a positive. So again, fixed on your end. So then t is -1. So then on this side, we have t is 4 seconds. So then this answer would be inadmissible because we cannot have time less than 0. So then we only are interpreting that second value for t is 4 seconds. And our interpretation would be that when the height is equal to 0 at time 4 seconds, that means that the ball has now landed on the ground after it being thrown from the cliff. Now for part B, we want to find the axis of symmetry, which is going to give us that maximum height. So now we know that we have at point 4 here, or at T4, we have a point. So for the axis of symmetry, oh, and we also have technically a point at -1, even though we're not going to count it for this word problem, but for a parabola and that formula, it does exist. So then now I look at A, I just want to get a sketch of my graph first. Because A is negative, then my parabola is opening downwards, which is what I would expect because I have a maximum height. And I expect it to look something like this. And that would also make sense because I have a y-intercept there, and the ball is thrown from a cliff. So it's not starting at height 0. It's starting at a height already, and then it lands on the ground, which is that height 0. And so my axis of symmetry, which would fall between these 2 points, needs to be an equal distance apart from both of these. So here, for B, we would have to add these two and divide by 2 to get 1 point, or 3 over 2, or 1.5. And so I know that at time 1.5 seconds, the ball reaches its maximum height. So my axis of symmetry first. So make sure you are answering all parts of the question, even though I know we're excited to go get to the second part and answer the maximum height. You were asked for the axis of symmetry, so please include that as x is equal to 3 over 2. And then for the max height, we are essentially calculating h of 3 over 2. And if you try, you should get 31 and 1/4, or 31.25 meters. And this one was seconds here. So at time 1.5 seconds, the ball reaches the maximum height of 31.25 meters. And oh, we already did that for C as well. Oh, so B was finding the time, so we found the time. So then this is part C. We found the maximum height as well. And interpret it in relative to the cliff. So we can kind of assume that as the object is thrown, so let's say my cliff is here, the object is going to go a little above before landing back on the ground. So it will um, actually reach a height higher than the cliff after being thrown from the cliff. And for the interpretation there could also be that you add maybe the person throwing the ball through it upward motion. That's why it reaches the maximum height. Because compare that if you are standing on a cliff and you just throw the ball downwards. Then your function here would be something like, uh, or your graph results would have the maximum here and it would just be going down. So because our maximum height is not at the cliff, then we know that the ball was thrown in an upward motion, so it reaches a height even higher than the cliff's height later on. And our last question here, for how long is the ball above 6 meters? So for this, we want to essentially uh, find the point of interception with the line y equals 6. And we know then uh, any time from the starting time until that height 6, the ball will be at a height that's above 6 meters. So I will set h of t as equal to 6. And here you're just solving for the equation. So I'll give you a bit of time to try this and then come back and check your answer. Okay, so I started by setting the two functions as equal, and I also expanded my factored form to standard form. And then I moved 6 to get a quadratic equation equal to 0 so that I can apply the quadratic formula. Because here, there's nothing you can factor for greatest common factor, and they're not really easy numbers or friendly numbers, so I would just skip to quadratic formula right away. And you should have got these two answers, and the negative answer will be inadmissible, so we only accept that 3.75 second answer. So going back to our graph, that means that the time here is 3.25. So between time 0 to 3.25, and um, not inclusive of 3.25 because we're asked for how long is the ball above 6 meters, not uh, above and including 6 meters. So we would just say for any time between 0 to 3 point and before 3.25, the ball is above 6 meters. And you're asked to give the time interval. So that would be our set notation here. So domain and range. So we would write t is in the set of real numbers, and t has to be between 0. It can be 0 because at time 0 it's on the cliff, so it's above 6 meters. And so just on this part, make sure that we are using just the less than sign and not less than and equal. And that would be your answer in set notation. And that's the most correct way. While you can always describe in words, with math and set notation, there's no question about like your answers or your results. So now our final question for this lesson. We have a gardener who is creating a flower bed, and here we have area, but we have seen a similar question before where there is a restriction on the side lengths with respect to one another because we have, for example, a restriction on our total area. So here you're told that X is the length of one side and the other side is determined so that the area follows this model for feasible X values. So that means that the other side length is dependent on that first length. So here, find the zeros and state what they mean. So here for the zeros, if X is equal to 0, or sorry, if we set the A of X as equal to 0, that means we want an area of 0. And this would happen when we have no side length. So essentially when x is 1 or x is 5, um, we have our restriction, which means that this condition is no longer met. So that when one side length is 1 or 5, it is no longer feasible, or the other side length is no longer feasible for this formula. So they would be inadmissible values in this example. Now, for B, we're asked to determine x so that we can find the maximum possible area. So maximum, that's my vertex, so we can, so in this case, because your original formula is given to you in factored form, I wouldn't switch to vertex form because that requires 2 steps to go to standard form and then switch that to vertex form. So here, I would probably think it's best we will find our axis of symmetry and use that to find our vertex. So my axis of symmetry will be between 1 and 5. So I hope we see that it is at 3. So it's 2 apart from each. So if we have 1 and 5 here, we would have our axis of symmetry at x is 3. And to find the maximum possible area, we have our x value of the vertex. So now we will just substitute this into a. So a of 3 is going to be -4, 3 minus 1, and 3 minus 5. So we should get 16 here. And that would be in meters. So meters squared. So therefore, maximum height, so write a full sentence, but the maximum height is achieved when one side length is 3 meters and the maximum, I think I said height. The maximum area is 16 meters squared. Now, here we're asked, suppose the gardener needs at least 6 meters of area. For which values of x will the garden meet this requirement? So, similar to above, we want to set this function as equal to 6. So, again, just to have like a little sketch, I know it's going to look like this. So, take a moment now, especially because we've seen the previous example, try this on your own. Okay, so here we are expanding first to that the standard form, and setting a of x as equal to 6. And now we can find an equation that equals to 0, and I will apply the quadratic formula. So one step here, you could have factored out -2 from here and made your ABCs a little smaller, but because I kind of knew already that I was using quadratic formula, it didn't matter. You can just skip to this step right away and let the calculator do the work. So then we get we get x as 1.42 or 4.59 meters. So interpreting the results here, that means that if my length is 1.42 meters, my area will be exactly 6 meters squared. Or similarly, if one side length is 4.59 meters, my area will be 6 meters uh, squared exactly as well. But we're asked that he needs at least 6 meters squared. So assuming that those 2 points are approximately here at, or hold on, let me do maybe here, y equals 6, then we want values that are uh, greater than 1.42 and less than 4.59. So using set notation here, I will write x belongs to the set of real numbers, and my restriction here is x has to be greater than 1, oh no, 1.42, and has to be smaller than 4.59. Okay, and in this case, just so you see it as well, my range for this particular set would be a of x is greater than 6. Okay, and that would be all the values of a of x greater than 6 because that's what the Gartner requires. So that's your domain and range also in set notation. And again, make sure you have a concluding statement to show your thinking with with language, so like with written words. So I know that you have also interpreted the results based on the word problem. And those were some applications for the standard form, or sorry, the factored form. So the key thing with these problems was that X isn't necessarily representative of the number of sales or the price of something or like one specific quantity. X was rather the change in um, one of your variables. For example, in the first one where X was the number of $1 increases and also the number of sales that we were like losing, which was correlated. Um, or for example, in this last question where we have a restriction on one side length based on the other side length. So these scenarios kind of give us factored form. So as you work through the other problems, you'll be more familiarized with word problems where a factored form is best to use. So especially when we need the zeros, I hope you know that factored form is our best choice there because we have the zeros right away. And that was a wrap up for our standard function, and I will see you all next class.